does not want statistics after dinner? Right after the full caffeine crush, and everyone's slowing down their metabolism and getting a bit of intermediate statistics in their life. I can see you hiding back and forward and over. Sure. Alrighty then. So, if I can have everyone's attention for a bit, I know that the previous SLUs and exercises are super interesting, but I'll be fast, and these are really, really important concepts. I promise I'll try and make them as painless as possible. So, very quickly, everyone has an intuition of what correlation is to a point. We have these concepts of how things vary together. A lot of it is quite intuitive, and a lot of it is dangerously intuitive. So I'm not going to talk about any of implementation details, how to use pandas. It's actually super easy. It's like 2 lines of pandas. So I'm actually going to talk about the concepts instead. What we're going to talk about today is pretty much just this. How does the age of these kids have a relationship with their height, right? So we might think about that as starting with covariance as the most intuitive one. What is the relationship between the kid's age and their height? We might say, okay, we have a few kids, we have a few ages, we have a few heights. We expect that as the ages go up, the heights go up, but there's not a one-to-one relationship. Some older kids might be shorter, right? So what we effectively have in this little data set is something like this. I hope everyone can see these dots, but essentially they're dots that are going up, but every once in a while they stop going up and they do these little curves. One way to think about how together these two things move is to use covariance. And covariance is a ridiculously simple expression. It's pretty much how much is the sum of the thing minus the average of the thing. I'll illustrate that. This is the average of the heights and the average of the ages, all right? That little cross in the middle. If we take a particular kid, let's take this kid number 6. He's 12, he's 1.70 meters. So his age is bigger than the average. His height is also bigger than the average. So as you can see, the sign of that will be positive, right? So if we plot it here, it's like this blue square. It's positive and positive. Now we take a look at another kid, and it's a 9-year-old, but that 9-year-old is only 1.39 meters. So, okay, he's actually shorter than most kids of that age group, and therefore he's going slightly under the average. So it's downwards, and we intuitively think of that as being a negative something relationship, right? And so the correlation graphically, if we do this for all of the kids at the same time, is a really, really simple idea. It's just this area, right? The blue squares minus the red squares, and then we divide by the number of kids so that the number gets slightly crushed down. So that makes for a really, really super intuitive way of thinking about things. And this is how lots of people used to do things, of thinking, okay, the relationship between the kids' heights and the kids' age is what? And then you can go to your boss and say, oh, it's 115 centimeter years. And that's as correct as it is completely useless, right? What the hell is a centimeter year? You don't have any intuition for that. So there are another bunch of problems with covariance and why in practice you should probably never use it, which is we're talking about centimeters, but in some parts of the world, they don't use centimeters. That's too weak. They use freedom units, or feet, I think they call them. So you can see that, okay, some kids have 1.20 meters, but then the other ones with the eagle, they've got 3.93 feet, they've got 4.10 feet. But the relationship between height and age should not have changed, right? It's just we changed the unit. However, if you look at the expression, this component here of heights, that's actually in whatever unit we are using. So what ends up happening is that the covariance in centimeters is 115, but when we use feet instead of centimeters, we've got 3.8. And that's horrible, right? The relationship between things shouldn't depend on the way that we measure them. So yeah, that's having a relationship that changes with the scale is a special kind of stupid, so we don't like that. And we are going to move to something that's a bit more practical. Correlation is just covariance. So what you've just seen, that super simple thing, divided by a normalized version of the variance. So the variance is how much something changes. So you might imagine that before we had a bigger covariance when we were in centimeters, but the variance was bigger as well. So that bottom bit, ignore the math, it's not particularly scary, it's just compensating for that. And if you want to do the geeky math version, you've got feet years over years squared times feet squared, and then you've got this, and if you simplify it, you get to a Stewie Griffin of victory is mine, because correlation has no units, which is a beautiful thing. Correlation is not in feet centimeters squared, it's a pure number that's between -1 and 1, and it doesn't have any units, which is a fantastic thing. So, quick summary of that. Correlation has no units. It's called adimensional for that. None of this centimeter year nonsense. The value takes place between -1 and 1, so you don't get this 400 correlation, which we would not have an intuition for, and it's not affected by the change in scale, which is super useful. So if we want to do a quick check of that, correlation metric system between those two things would be 0.92. Correlation in imperial units would be 0.92 as well, because correlation does not depend on the way you measure. Cool. Yay, correlation. Now, little confession bear. When I say correlation, and this will happen in your day-to-day lives, what I mean is Pearson correlation. It's perfectly fine. You will say correlation when you mean Pearson correlation. The people around you will say correlation when they mean Pearson correlation. But do not forget that there are multiple types of correlation. Pearson is just one of them. I'll go into what this means. The ones we will talk about in the academy are Pearson correlation and Spearman correlation. And they're both useful in different ways. The Pearson correlation is exactly what we talked about. It's that relationship divided by the variance. The Spearman correlation is exactly the same thing, but instead of taking the heights, we take the place on the podium of their heights, right? So the tallest kid becomes 1, the second tallest kid becomes 2, the third becomes 3, or in the other direction. So it's just the rank, what was their position in the podium, and then everything else works the same. So you'll very often see like complicated things about Spearman correlation, but Spearman correlation is just the Pearson correlation of the rank. All there's to it. Really, really simple idea. And here's an example of the actual heights, and here's the rank of the heights, right? Here. Just line that up. So why am I bothering you with a new concept right when you've just discovered Pearson correlation? You've finally thought, okay, I'm going to use this to predict the stock market. I'll be rich. I won't even need to finish the academy. I'm just going to make money. The reality is that Spearman is quite useful for things like this. Imagine that you're trying to do something and trying to capture the relationship of this and trying to see how that thing varies with that thing. Doesn't really matter what it is. You with your eyes, because of what Manuel was talking about, you can just look at it and go, that varies they vary together a lot, right? So one goes up, the other one obviously goes up. There's no doubt in my mind about it. But if you calculate the Pearson correlation of that, it's just 0.95. So you'd actually expect, if you hadn't seen the plot yet, to see it going up and down. Whereas the Spearman correlation, because it just needs the rank, looks at that and says, oh, that's 1. That's purely, if one goes up, the other goes up, because it only cares about the rank. So in certain circumstances, you do care about this. The other circumstance is Pearson correlation is super vulnerable to outliers. If you have a bunch of houses and a bunch of, I don't know, if you have the price of the houses and the number of rooms, they're probably very correlated. But then if Barack Obama moves into one of those houses and the price becomes 10 million because Barack Obama was there, then the correlation actually gets messed up because of one single point. Whereas the Spearman correlation holds very well. That's the other big advantage. Cool. The other thing that you can do, which is pretty cool, I'll give you a practical example of this. So let's take the exact case of housing prices, is when you have a bunch of things, in this case, the poverty rate, taxes, school quality, road quality, the price of houses, a bunch of other things. And you want to figure out what are all the correlations between all of these things at the same time. You can do that with 4 letters in pandas, which is to write .corr, 5 characters. And you can do something like this, which is everything against everything, show me all the correlations. And because it sucks to, go ahead.
Data is a data frame.
Yes, that is, sorry, I should have pointed out. So data is this data frame. Doing data.corr just goes, oh, calculate all the correlations of everything against everything. Quick caveat, if your data set is big, this will make your Mac turn into flames. It will make your Windows computer explode. So depending on what machine you have, you'll have a different insurance problem. But because it's a lot of computation in just one line. The one quick caveat about this is that it sucks to look at correlation matrices this way. So normally what we do is we use a little visualization that makes high numbers green, low numbers red, and we get something that's oh, good. That is actually friendly to our visually impaired friends, and it's not green to red, it's black to white. So you can immediately look at that and say, oh, okay, here are some really negative correlations between house price and poverty, which makes sense. Here are some really high correlations between that and that. And because it's visual, it's really easier to interpret. It's just an easier way to do it. And in your learning notebooks, it explains exactly how to do this. It's also a couple of lines of pandas. So this is all great. And now is the part where we get to use all of this stuff in science. And now I'm going to quickly tell you a real case of one thing that showed up in nature of how correlation gets used. So I'll get rid of the bear because it's distracting. The story was as follows. A few scientists decided to test a hypothesis that sleeping with the nightlight on made kids myopic. Okay? So they took a bunch of kids and they said, okay, we'll get a big sample of kids who sleep with the nightlight on. We'll take a big sample of kids who don't sleep with the nightlight on. And then we'll follow them for a bunch of years. We'll spend lots and lots of money on this particular research project. And we'll see whether those two kids evolve into different directions and one of them gets myopia and the other one does not. Seems like a fair test of it. And the results of that myopia test ended up in one of the most prestigious journals in the world. It's clearly showing that ambient light at night caused myopia, and it was any p-value. You couldn't contest the number of samples. You couldn't contest anything. It was rock solid proof. Minor caveat is that this is absolutely nonsensical. And the reason is that, as you might imagine, if parents are myopic, they don't see very well in the dark, yeah, which means...
But the numbers are right.
No, yes.
The interpretation is not correct, but the numbers are...
Exactly. So the fact that correlation exists means that we does not mean that we have...
Causation.
Can I have that again, please?
Causation.
Can I have that again, please? Hallelujah. So correlation is not causality. Correlation is not causality, and that's the crucial thing. You might get really strong correlation numbers, but it in no way implies that you have found causality. You might have used that to find that it's worth interpreting something. Maybe there's a signal there that is worth exploring, whether, oh, let's see whether their parents were myopic. Maybe myopia causes nightlights. But determining that there's a correlation means that one causes the other is one of the main, most frequent mistakes in data science, and God knows in finance. Last couple of slides. So my favorite slide, the divorce rate in Maine is incredibly highly correlated with the per capita consumption of margarine across the world. Actually, 99.26% correlation with an R of 99.2. US spending on space science and technology highly correlates with suicides by hanging, strangulation, and suffocation, with, again, 99.79%. And this is the kind of nonsense that's used in finance all the time, as unfortunately I have seen a bunch of hedge funds believing that correlation between two things means that they should put money into one and not the other, which has led to a bunch of disasters across time. So if this talk was useful for anything, it's just to remember these three things: that correlation is not causation, that there are multiple ways to calculate correlation. One of them is Spearman, which is more robust. And to understand that there's a big difference between what is observational data, which is data that you can control, experimental data, which is data you can control, and observational data, which is data that just exists out there in the wild. The reason why that is important is because if they had taken a bunch of kids at random, forced half of them to sleep with a nightlight on, which obviously has its own problems, and forced the other one to sleep without it, then the experiment would have been perfectly valid because that would be experimental data. You were controlling everything with randomization. If you were using observational data, you're running into all of these problems. So those are three main takeaways. And yeah, I just want to leave you with this. I'll actually leave it on for a bit and go to your exercises and have fun.